before we get back into regression, let me go ahead and just point out a few other things about this chi-square thing. One thing to notice with this table, with this density curve, this chi-square distribution, is that it's not symmetric. It's not like a normal curve. It's not like a t-distribution, which are both symmetric. This one's got a right skew to it. Chi-squared can never be negative. It's got to be positive. That's one intuitive reason why it's got to be right skewed, and it theoretically can have pretty high values. Again, you've got degrees of freedom. Just a quick reminder how to use the table. The df in the context that we were just talking about, remember, was the number of rows minus 1, r minus 1, times the number of columns minus 1, written c minus 1. That's the degrees of freedom in this context. Again, that's kind of a mysterious thing. What does degrees of freedom mean exactly? Kind of a strange term, mysterious idea. Just think of it intuitively. When your table's small, when your R and C are relatively small, it's kind of like you've got less detailed information in a sense. The degrees of freedom being smaller gives us, well, let's see, with the chi-square, how does it work? The smaller the degrees of freedom, the less skewed it is, okay? I'm not sure if that's real intuitive. I'll show you a picture that I had up there and that I jumped over before. Here's kind of the way the distribution looks. There's with a small number of degrees of freedom, like 1 perhaps. This might be 2 degrees of freedom, this might be 3, and this might be 4. It does, initially with a small number of degrees of freedom, not have any kind of maximum to it. But as the degrees of freedom gets higher, you do get a maximum point to the graph, and the graph spreads out more to the right. I'm not sure if there's a real intuitive way to think about that, but that is how it's related to the number of degrees of freedom. In the context where the degrees of freedom is 1, R and C are both 2, it's actually the value of the chi-squared statistic is equal to the z value squared for population, for sample proportions. If you calculated the z-statistic to compare two population proportions with two sample proportions, you get the, and then if you took that statistic and squared it, you get the value of chi-squared in the context where you have 1 degree of freedom. You can use a spreadsheet to calculate the p-value in this context. However, it doesn't work on Google spreadsheets at the moment. Okay, here in November of 2015. I tried it this morning, it didn't work. It does work on Excel, however. If you use this function here, CHITEST, that will calculate the p-value. On Excel, I haven't found an easy way to do this with Google Sheets at the moment. And you can also calculate the corresponding value of chi-square, or if you know the p-value, using a function called chi-inverse. I want to show you this right now on Excel instead of Google Docs. Here I have the actual and expected data for the same example from the first half of the lecture. If you type equals CHIDIST, and then type in the value of the chi. Actually, this is working differently than on my particular computer. When I use CHIDIST on my computer, I highlighted the cells of the actual data values, then I put a comma, and then I highlighted the cells for the expected data values. And it computed chi-squared just from that. So on this computer, it's working differently, even though it's still Excel. They want the value of chi-square, which they're just labeling x here, and they want the degrees of freedom. For our example, we got 2.997 for the value of chi-square, and we had 2 times 1, 2 degrees of freedom. So this should give you a value between 0.2 and 0.25. 0.2234651. Okay? That's the p-value. If you use chi-inverse, what you're trying to find is the corresponding chi-square value if you know the probability in the right tail. That probability label there means the right-tailed area. If, for example, we want to know what chi-square value would give us a p-value of 0.05. That would be at your typical boundary for rejection or not, based on 2 degrees of freedom. We would have needed a chi-square value of, should be bigger than 3, maybe 4 or 5 or 6. Oops, put 2 commas in there. Should be bigger than 3, maybe 4 or 5 or 6. It's close to 6. We would have needed a chi-squared value from the formula of close to 6 to get a p-value of 0.05 or smaller. Bigger than 6 to get it smaller than 0.05. Our value is close to 3 for this example right here. Okay? All right, let's go back to regression now. I got 2 things I want to do with regression today. One is I want to review the SS formulas and their usage. We did verbally talk about these last time. I want to review the usage of these things on the spreadsheet to remind you how to use them. And secondly, I want to do something new, and that's to compute something called the regression standard error, and use some some Google Docs spreadsheets, Google Sheets features to actually calculate the slope of the intercept of a sample regression line, where you're taking a simple random sample from a wider population. So let me write these formulas on the board, and then we'll use them. You won't have an electronic assignment here over Thanksgiving, but I am planning on an electronic assignment next week. We're focused on the shortcut formulas on the far right. SSXX is the sum of the x squareds minus the sum of the x's, quantity squared divided by n. SSYY is the sum of the y squareds minus the sum of the y's, quantity squared divided by n. SSXY, the shortcut formula, is the sum of the products x times y minus the product of the sum of the x's and the sum of the y's divided by n. Once you've got those, the correlation is SSXY divided by the square root of SSXX times SSYY, and the slope of the regression line is SSXY divided by SSXX. So we did practice this back in the first few weeks of class. Just want to practice it again in a Google Docs spreadsheet. This is related to one of your homework problems, actually. Okay? So essentially, I am doing one of your homework problems here. At least in part. Maybe we won't do the whole thing. It's good to make a row for the sums so that we can use these summation formulas. I will also calculate the other statistics, the means. I should probably call this sums. Means, standard deviations, and I'll use Excel's built-in equals correl to calculate the correlation as well, so we can check answers. Ultimately, getting the slope and the intercept as well with the formula from the book, so we can check answers. Thinking about these formulas, I'm going to need to make a column for x squared values, y squared values, and x times y values. I've got columns for x and y themselves. Make a column for x squared values. Make a column for y squared values. Make a column for x times y values. All right, think about this with me here. So x squared values, I'm in cell D2. I'm going to do equals B2 squared. No dollar signs necessary. I want this to copy and paste and do the appropriate thing. Do B3 squared, then B4 squared, etc. Since I didn't use dollar signs, I can also copy and paste this column to the next column. Highlight the entire thing here, do a Control-C, and then go to the column E and do a Control-V for paste. That's going to update the B's to C's. So instead of doing equals B2 squared, I'll do equals C2 squared in the top row of this column. 40.1 squared should be what goes in this first spot. 40 squared is 1600. So this is going to be a bit bigger than 1600 for the first one. 1608. Okay, it is doing the right thing. I don't want to copy and paste to the next column because in the next column I need to multiply each x by the corresponding y. Equals b2 times c2, what would be what goes there. There we go, copy and paste that down. Now we are going to want to add up the columns. Equals sum will add each column. And I can copy and paste the formula or click and drag it over. So I first add up the x values, get that, then click and drag this over, copy and paste it over to add up the other values in these other columns. Now let's compute the SS's. Doesn't really matter too much where I put them. SS, XX, SS, YY, and SS, XY. Use the shortcut formulas on the board. You just got to identify the appropriate spots. I think I'll go ahead and write on the screen here. This is the sum of the x's. This is the sum of the y's. This was the x squared column. That's the sum of the x squareds. This was the y squared column. That's the sum of the y squareds. And this was the x times y column. This number is the sum of the x times y's. So, looking both on the screen there and on the board, what goes in cell E10? I've got to do that minus this divided by that. Sum of the x squareds, careful, is in cell D8. That's where you square the x's first, then add. The sum of the x's, quantity squared, where you add first, then square, would be taking what's in cell B8 and squaring it. Then divide by n. We have, what, 5 years here, I think? N is 5. Yep. N is 5. Divide by 5. Be careful about order of operations if you're doing this on a calculator. You'd want to square this first, divide by n, then do the subtraction. You calculate this fraction before you do the subtraction. Excel knows, or the spreadsheet here knows, to square and divide first before doing the subtraction. It's programmed to do order of operations correctly. SSXX is 10. How about that? Came out to being exactly 10. You shouldn't expect that to typically happen. SSYY do the same thing. The sum of the squared y's is this thing here, minus the sum of the y's, quantity squared, divide by 5 again. Using this formula, that's not going to come out to a whole number, as you can see. Finally, SSXY formula. With this, you're multiplying the x's and y's first, then adding. That's the last column, column F. F8. Here you are adding the x's and y's individually first, then multiplying the resulting sums before dividing by n. So we have this times this divided by 5. And again, if you're doing it by hand with calculator help, you'd want to compute this fraction first before you subtract. That's the way the order of operations goes. How about that? This is coming out to a whole number as well. Let's now compute the correlation and the slope, B1. Using the formulas on the board, the correlation is this number divided by the square root of the product of these two. Compare that with what's on the board. SSXY in cell E12 divided by the square root of this product, which comes from cells E11 and E10. Correlation is pretty close to 1. This is a very strong positive linear trend. R squared would still be close to 1. The slope, finally use this formula as SSXY divided by SSXX, 23 divided by 10, which will be 2.3. All right, Let's now confirm the answer with the other formulas. Let's find the means, x bar and y bar. That's x bar and y bar. Let's find the corresponding sx and sy, the standard deviations, equals stdev. Copy and paste that over for the y's. The correlation then is with equals correl, 2 R's, 1 L. Do the first column for the x's, then put a comma, do the second column for the y's. Now let's do the slope and intercept using the book's formula. The correlation is R times the ratio of sy divided by sx. You don't need parentheses here. That's the book's formula, right? B1 is R times sy over sx. So this should come out to 2.3, and you can see it does. Matches the 2.3 over there. The correlation matched as well. That's all good. In either situation, to find the intercept, the quickest way based on what we have here is to do the same thing we did before. Take y bar minus b1 times x bar for the intercept. Y bar is 45.26 minus b1, which is the slope, which is found, times x bar. The y-intercept is, in this case, is negative 4,566.24. All right, so that was part of my goal for today, is just to review how to do all that. We did that back a couple weeks into the semester. Just want to review that you get the same thing and review how to use the formulas. We also know we can get the slope and intercept of the regression line by making a scatter plot and including the line in the regression equation on the scatter plot. But what I want to show you today is something new now. A new way to get the slope and intercept. And in fact, especially it's a useful way of getting the slope and intercept in the context of inference for regression, where this is sample data from a wider population. I am going to go ahead and apply it to this example where we're looking at, by the way, research and development spending, National Science Foundation data for different years and different spending amounts in billions of dollars. This example is not really an ideal situation to think of in terms of inference, to take sample data and infer information about population data, because really, in a sense, we do have population data here. This is the NSF spending for these years, okay? There's no population data to do inference for, really, unless you're thinking of it in terms of extrapolation beyond these years. So this is not really, as a word of warning here, this is not really an ideal situation to use the Chapter 10 regression model for. I'm going to go ahead and get the output anyway, as if it's a good situation for that, just to illustrate how to get the output. This is a little complicated. You might want to take notes about this. If you don't take notes, you'll want to re-watch the video. What you're going to want to do is you're going to want to go to add-ons. Tab up here that says add-ons. And you're going to want to go down to get add-ons. What are add-ons? They're extra things that you can add on to the spreadsheet, to Google Sheets, that will help it do more things for you. Pre-programmed stuff, apps, if you will, that will have it do more things for you. And there are lots of add-ons that are out there that can do lots of different things, probably make a lot of neat graphs and that kind of thing. What you want to search for is something called XL Miner, M-I-N-E-R, miner as in digging, not miner as in minor key. Can you see that? XL Miner, that's what you want to search for. There it is, XL Miner Analysis Toolpak. And you want to go ahead and add that. It says free, you're not going to have to pay anything. Click it, click allow, does a little work. It's now in there. You now have the capabilities in this XL Miner Analysis Toolpak. One of these capabilities includes doing some fancy stuff with regression. I'm about to show you. Go back to add-ons now, and now the XL Miner Analysis Toolpak is there for you to use. Click Start. Got this down? XL Miner Analysis Toolpak under add-ons. Click Start. It's working. It gives you, once it's done the work, a bunch of different options for things you can do, statistical things. We want linear regression right here. Again, you're going to want to be writing this stuff down or else rewatching the video. What you should do next, I almost always click this labels box first. What does that mean? That means in my cells that I'm going to highlight, that I'm going to do a linear regression with, I want to include the labels. These things, the year for X and the spending for Y. I want those to be included. That's a good idea. And you want to have labels there. If I highlight the Y range, including the label, like this next, C1 through C6, the label and the numbers, and then click on this box that says input Y range, it shows up for me there, C1 colon C6. I could also just type that. If next I highlight the X values, including their label, B1 through B6, and click the input X range, that shows up there as well. Again, I could also just type that. The next thing I do is I go down to where it says output range. Well, click on residuals, click on residual plots, and then go down to some spot in the spreadsheet here below all this stuff, maybe say cell D16 there, and click on the output range box after I click on D16, or else again just type D16. The output for what XL Miner does here is going to be come out in the spreadsheet in such a way that the upper left corner of the output is going to be in the cell D16, where I just clicked. It's going to be the upper left corner of the output. You're going to see the output down to the right of that. Ready? I'm ready to click OK. And lo and behold, I get a bunch of stuff that, if you've read deeply into Chapter 10, should look familiar. The summary output here, this stuff, plus some graphs over here, residual plots, a residual plot, is the output we want for this XL Miner Analysis Toolpak for linear regression. And the only thing I want to focus on today is that you can find the slope and the intercept and the correlation in this output. There's the slope there, that's B1. There's the intercept, that's B0. And, well, there is the correlation, R. It's called multiple R up here. In multiple regression, where you've got more than one explanatory variable, they call it multiple R. Don't worry about that here. We're only doing one explanatory variable. That is the same as our correlation. And its square, R squared, the coefficient of determination, is right here. That's R squared. Okay? Now, what's this output good for? It's good for doing inference. Again, thinking of this regression line as a sample regression line and using it to make predictions about the population regression line and also population data. Again, this situation with the NSF spending as a function of the year, it's not really an ideal situation for that because, again, for those years you really do have population data. So it's not necessarily a good situation for inference, to take information about a sample and make predictions or inferences about the population. But I do want you to know you can get the slope, intercept, correlation, and squared correlation from this output here initially. These numbers do match what we got before. And this is part of your homework assignment for next Tuesday. So turn it in. Essentially, I've done part of, we're almost done here, part of exercise 10.5, page 534. There's something else in exercise 10.5 that I want you to know as well. In part D of that problem, or part C and D, you're supposed to calculate something called the regression standard error, S. And the formula for S is this. Square root of SSE divided by n minus 2, where SSE, like we talked about last time, is the sum of the squares of the errors, sum of the squares of the residuals. Divide by n minus 2, where n is the sample size, the number of points, and then take the square root. That number, which you can calculate using the formulas we've already used, is in this output as well. It's this number up here. This is the regression, so-called regression standard error. S. And what that's a measure for, this is the final thing I'll say today, what that is a measure for, an approximation for, is in this regression model, it's an estimate for this number, sigma, which is a standard deviation that the model assumes holds for all the values of y for any given x. Imagine a given x. Remember we had that example with the stacked data points? The TV watching? For any given x, you've got a certain mean for the y's and a certain standard deviation. There's a certain amount of spread in the y values that's modeled using a normal curve with a certain standard deviation. This S, this regression standard error, approximates that sigma. And you're going to see that come up not just in this problem, but also another problem. I might give you a few more hints about it over email. Okay? That's it for today. Have a good Thanksgiving.